we already covered the discussion on graphite furnace AAS and also flame AAS, and they are applicable to so many elements like tabulated in the periodic table, but which is including the metalloids. But what if you want more sensitive methods for metalloids? Okay, we have one method and one instrument, what we call as hydride generation atomic absorption spectroscopy. Okay, this HGAS, not to be confused with mercury, is very suitable for metalloids inside periodic table. Okay, first of all, okay, refresh your inorganic chemistry. What are metalloids? Okay, metalloids in periodic table are the elements, okay, tabulated in group 14, 15 and 16 as shown here. Okay, as shown here, we have 1, 2, 3, 4, 5, 6, 7 elements, okay, which are semi-metals. Metalloids means that it is semi-metals, okay, means that it's half metal and sometimes it's not metal, okay, according to their valency. Okay, and hydride generation AAS is also suitable for, okay, selenium, okay, and very famous to be used with arsenic. Okay, now the question is that what is hydride? So refresh back your basic chemistry. Hydride is the hydrogen anion, means that there must be something happening to make it into hydride. So what are those? Okay, so hydride generation AAS is usually applying the reduction of the hydrogen. Okay, what makes it reduce? So we have to apply certain chemical reagents. Okay, this is the most unique feature of hydride generation AAS as compared to flame AAS as well as graphite furnace AAS. In those two methods, we don't have chemical reaction at all. We depends on the atomization of the elements using very high temperature using flame or either graphite tube, and usually the temperature is around 1500 and above, okay, which may not be suitable for arsenic sometimes, okay, at high temperature. Okay, why? Because at high temperature metalloids, okay, they tend to be giving low sensitivity because in the first place sometimes they are not metal, okay, because it's like the middle of metals and non-metals. Okay, so as stated in APHA 3114 method, okay, this is the example of arsenic and selenium determination by HGAAS. Okay, why metalloid elements can be subjected to this method? Because they can form volatile covalent hydrides which can be separated from the main matrix. Okay, main matrix such as those metals that cannot be reduced by this chemical reagent. Therefore, it is more sensitive. Okay, because the metalloids are the one that can only be reduced by sodium borohydrate. Therefore, it can be separated from the other matrix interference. Okay, let us see on the reaction. Okay, so standard method for hydride generation currently is by sodium borohydride. Okay, it is using the concept of reduction. Okay, so in the instrument you can imagine, okay, how can the instrument mixing two reagents together? So we will see what we call as flow injection system. Okay, flow injection system is the one that will flow in the reagent. Okay, here is sodium borohydride and hydrochloric acid to be like flowing inside the AAS. Okay, so after you mix those 2-3 reagents, you will have a metal hydride here. means that it's reduced and also will be reacted with your metal. Okay, what then? Okay, the hydride you produce during the chemical reaction will be decomposed in a heated quartz tube. Okay, when it is heated, it is heated. It will further produce the atom. Remember, we are still talking about atomic absorption spectroscopy. So we will produce atom. Okay, so in this case, yes, heating is still needed to decompose the hydride. Okay, and usually the temperature used is 900 degrees C. Okay, it is not as harsh, it is not as high temperature as compared to flame AS and graphite furnace AS. Okay, what happened after the decomposition of the hydride and production of atom? Same thing with previous AAS, it will go towards the radiation absorption given by the same hollow cathode lamp from the same element given by hollow cathode lamp or EDL. Okay, what are the elements usually suitable for hydride generation AAS? Belongs to group 14, 15 and 16 as well as these metals. Okay, specifically for arsenic and selenium, this is stipulated in APHA method. So means that this is a standard method. Okay. So what? Let us see how the hydride generator looks like. Okay. So imagine that this is actually attached to your instrument. Okay, we have sodium borohydride in one flask, and then we have hydrochloric acid in one flask. Okay, they will be mixed together using the peristaltic pump. Okay, so that it will react and flow inside the heating element and further towards the optical cell. What is used in heating the quartz tube? Okay, you can use the same fuel oxidant flame here. Okay, or we can use electrified quartz tube heating element. This is applicable to more state-to-the-art instrument. Okay, so this is the one that is 10 or 15 years back. Okay. And then we have another method, what we call as cold vapor AAS method, or we abbreviate it as CVAAS. Okay, cold vapor, by the name itself, we can predict that the vapor that will be produced is cold, meaning that we don't need any heating, no heating. Why don't we need any heating? Because this system can work to produce atom of one element and only one element, i.e. mercury. Okay, this system can enable mercury to be atomized at room temperature, near room temperature. Why? Refresh your inorganic chemistry once again. So mercury has appreciable vapor pressure at room temperature, and therefore at room temperature itself it can be reduced towards atom. Okay, it can be reduced at room temperature, so we don't need any heating. But what if we apply heat to mercury? Easy, mercury will be vaporized and it is just gone with the wind. Okay, we cannot analyze any mercury when it is volatilized at high temperature. And that is why cold vapor AAS is developed for mercury. Because if you do mercury in flame AAS or graphite furnace AAS, you will not see mercury at all. Because graphite furnace and flame use high temperature, right? So it will vaporize mercury and it's just gone. inside the instrument without even absorbing anything or without being detected at all. So cold vapor AAS is specific for mercury only. Because of the disadvantage in graphite furnace and flame, it is actually an advantage for cold vapor because we can reduce to atom using only a reagent what we call as stannum chloride or tin chloride. Okay, what happened after it's been vaporized? Okay, it will be carried into the light path in the stream of air or noble gas, and the mercury atom can absorb the radiation given by the radiation source. Okay, this is also very suitable for methyl mercury as well. Okay, the metal will be eliminated and leaving behind the mercury atom. So this is also stipulated in APHA 3112B method, meaning that you have to use cold vapor AAS only for mercury unless new standard method comes in to enhance the efficiency, such as using SCP-MS. Okay, so this is how flow injection mercury system looks like. Okay, it is a very small instrument with a peristaltic pump and tubings all over the place, and this is the mixing chamber. Okay, the mixing is happening outside of the instrument body. Okay, let us see the video on the Perkin-Elmer flow injection mercury system. Okay. Okay, that's it. Okay, that's the instrumentation for flow injection mercury system. But nowadays, Perkin-Elmer produced one instrument that is workable for hydride generation AAS and cold vapor AAS. Means that only one instrument to do both, because they both need reaction chamber, right? So why not just combine them and produce 4 using